Who do I think I am challenging known physics? But anyways, something's been bugging me for about a week now. Something I've thought about in the past, but it just occurred to me on a Facebook post. Someone posted a diagram about forces and equilibrium, standard physics stuff. You kind of see it in every physics textbook if you ever had a physics class, or if you proactively just read a physics book. But I commented something that I thought was obvious. Actually, I said, force is a byproduct of equilibrium restoration, not the other way around. And Google's AI overview popped up when I searched it on Google and said I was incorrect. The restoration is the result of forces balancing out. And they gave me this whole explanation with an analogy about how eggs aren't a byproduct of a cake, they're an ingredient. And I mean, on the surface, that makes sense, but I'm thinking deeper, I'm thinking, wait. Because every example that I can think of, I keep ending up back at equilibrium restoration. Not forces creating equilibrium, but equilibrium restoration creating what we measure as force. So what I'm going to do is I'm going to walk through this because I think standard physics might have this completely backwards. And who am I? Just a regular guy. Who am I to challenge physics? I know. And I don't want to have to say equilibrium restoration every single time. So when I say equilibrium from here on out, I'm just talking about equilibrium restoration. So you don't have to correct me. It's not two separate things in this specific presentation. When I say equilibrium, I mean, the equilibrium restoration, which is basically, if there's a wave, the waves are moving and equilibrium is being restored. Everything is just in this universe is equilibrium restoration. Everything's trying to balance. And that's what keeps us alive. Because without that, we'd have determinism. And determinism equals death. So the first example I'm going to use is one that we all know, a helium balloon. Standard physics says there's a buoyant force pushing the balloon up. There's gravity pulling it down. The net upward force causes the balloon to rise. Force. But, hold on. Does the balloon need a force to rise? Does it? What if I told you the balloon rises because that's just what equilibrium looks like for that system? Equilibrium restoration. Think about it. Helium is less dense than air, right? Way less dense. So you've got this situation where something light is surrounded by something heavy. The helium surrounded by the air. And nature, reality, whatever you want to call it, has this tendency to arrange things with the heavy stuff on bottom and the light stuff on top. You can see a density tower for an example of that and proof. Not because there's a force pushing or pulling, but because that's equilibrium restoration. That's the state where everything is balancing out. So, dense stuff sinks to the bottom, less dense stuff rises to the top. That's just how density distributions work. And this can be proven. The balloon isn't being pushed up by some invisible force. The balloon is just existing in the configuration that is equilibrium for that density distribution. It's finding its equilibrium, where it's equal. And the thing that gets me is it takes no energy for the balloon to rise. Like, you're not burning fuel, you're not applying work, you're just letting go. And it rises. If there's helium in the balloon, it rises spontaneously. If force were fundamental, if forces were the cause, then rising should require energy input, right? But it doesn't. The balloon rises for free, for no cost. So there's no force that's causing it. because it's not fighting against anything. It's moving towards equilibrium. So right there, that's a first example. Helium balloon. Standard physics says buoyant force pushes up, but actually, equilibrium is just what less dense above more dense looks like. No force required. The second example is simple. A rock or an apple falls to the ground. Standard physics. Gravity, force, pulls the rock down. Force times distance equals work. Energy is spent. But is it? Well, let me ask you this. And I know this is big. Challenge in physics. Who do I think I am? Just a loser. But does it take energy for a rock to fall? Think about it. Like, really think about it. You lift a rock, that takes energy. You're doing work. You're fighting against something. You get tired eventually if you keep lifting the rock up. But letting go takes zero energy. The rock falls for free, at no expense, spontaneously, just like the helium balloon rises. Boop! Rises for free, drops for free. The helium balloon and the rock. So, what's actually happening here? Well, the rock and the earth are in a state of separation, right? They're apart when you lift it up. And that separation, that's actually disequilibrium. There's no equilibrium because you've lifted the rock up. That's why you needed a force to lift the rock up away from its equilibrium. The equilibrium state for the rock and the earth is together, in contact, because they're both mass, and mass creates this pressure gradient in the ether, or space, or whatever you want to call the substrate of reality. So when you've got a pressure gradient, things spontaneously flow down that gradient. Not because a force is pulling them, but because that's what pressure gradients do. They equalize. So the rock is falling, and the rock falling isn't being pulled by gravity. The rock falling is the equilibrium restoration process. The system moving the rock separated from Earth to the rock touching the Earth, where it can't go through the Earth because the Earth's not invisible. From disequilibrium to equilibrium. And here's the thing. Here is the thing. If you're at equilibrium, if the rock is sitting on the ground, it takes zero energy to stay there. No force is maintaining it. There's no energy expenditure, so to speak. It just sits there until something moves it, maybe a force. Because that's equilibrium. But if you lift the rock, if you cause separation again, that takes energy. Because you're fighting against equilibrium. You're creating disequilibrium. And the moment you let go, the system spontaneously aims to return to equilibrium. That's equilibrium restoration for free. So again, rock falling, standard physics says gravitational force pulls it down. But actually, falling is equilibrium restoration. No force required. Just the natural tendency of systems to move towards balance. So I also have a third example, and this one is maybe the checkmate. This is the important one. This is where it gets really clear. And we're going to talk about the second law of thermodynamics. You might know this one. Entropy increases. Disorder increases. System moves towards equilibrium. And the key part is this happens spontaneously, without any applied force. Let that sink in. Example, You've got a hot cup of coffee and you're in a cold room. The coffee cools down to room temperature eventually. No force is pulling the heat out. No force is pushing the cold in. It just happens spontaneously. Just like the helium balloon rises spontaneously, just like the rock falls spontaneously. That's equilibrium restoration. Hot and cold separated equals disequilibrium. Everything at the same room temperature equals equilibrium. If you open a bottle of perfume in a room, the smell spreads. I'm sure everyone's done that. Goes for anything that has a strong smell to it. It diffuses throughout the whole space. No force is pushing the molecules around. They just spread. Because concentrated perfume in one spot equals disequilibrium. Perfume evenly distributed equals equilibrium. So here's what gets me. Standard physics says the second law describes spontaneous equilibrium seeking. No force is required, just natural tendency toward balance. But then in other contexts, falling rocks, rising balloons, whatever, they say, oh no, that requires force. But why? Why would gases spreading require no force, but rocks falling require force? They're both the same phenomenon. They're both systems moving from disequilibrium to equilibrium. Coffee cooling is temperature disequilibrium. Moving to equilibrium. Gas spreading, concentration disequilibrium moving to equilibrium. Rock falling, spatial separation disequilibrium moving to equilibrium. Balloon rising is density inversion disequilibrium moving to equilibrium. Same process, same spontaneous equilibrium seeking for all of them. So why call it force in some cases and not others? Unless standard physics has it backwards. Unless equilibrium seeking is always the fundamental driver. And what we call force is just what we measure during the equilibrium restoration process. That would explain everything, including why the second law of thermodynamics works without forces, because forces aren't fundamental. Equilibrium seeking is fundamental. Okay, let me give you one more example, and this one really clarifies the distinction. All right. Buoyancy. This is a prime topic. Standard physics says water exerts an upward buoyant force on a boat. This force lifts the boat. The force equals the weight of the displaced water. Force, force, force. But let me describe what's actually happening. Yeah, I know, who am I to challenge physics? So anyways, you've got a boat. The boat has air trapped in it, air in the hull, air under the deck, whatever. The air is way less dense than the water. So you've got water underneath and the boat's on top of the water, but inside the boat, you have air. So the question is, what's the equilibrium arrangement here? The dense stuff on the bottom, the light stuff on the top. That's how it always works. So water goes below, air stays above. So the water isn't pushing the boat up. The boat is heavy, but the boat has air in it, and the boat's not heavy enough to push the air down below the water. The water just doesn't go up. The air just doesn't go into the water unless you have enough force to push it down. Because that would be a density inversion. That would be disequilibrium. So the boat floats because that arrangement, water below, air above, is equilibrium. No force is required. Just density distribution finding a natural configuration. And so here's where it gets a little interesting. Someone in this Facebook thread, the one I talked about, said, okay, but what about waves pushing a boat around? That's clearly a force, right? And I said, yeah, you can measure something, but if a wave hits a boat and the boat hits you and you fall over, we can measure that. We can say X newtons of force, but this is an important distinction. What's the cause of that measurable force? The wave is water that got displaced from equilibrium. Maybe wind pushed it up. Maybe a boat drove through and created waves. The point is, the water got lifted above the equilibrium level. And the moment that happens, the water immediately tries to return to equilibrium. That's equilibrium restoration. It falls back down. But because it has mass and momentum, it overshoots, creates another wave. That wave also tries to return to equilibrium, overshoots again. Now we have waves. So you get this oscillation, this wave motion as the water seeks equilibrium. And if the boat is in the path of that water in motion, the boat gets moved because the boat isn't heavy enough to withstand it, especially having air in it. And we measure that as a force. But the fundamental cause wasn't a force pushing the wave. The fundamental cause was equilibrium restoration. The measured force is the byproduct of that restoration process. See the difference? Force isn't the ingredient. Force is what we measure during the cooking process. The ingredient, the fundamental driver, is the equilibrium seeking. And so at this point, I'm seeing the pattern everywhere. So, I started going through examples in my head. Every physical phenomenon I could think of, I kept ending up at the same place. Equilibrium restoration. Equilibrium. Falling rocks. Equilibrium restoration. Rising balloons. Equilibrium restoration. Heat flowing. Temperature equilibrium restoration. Gases spreading. Concentration equilibrium restoration. Magnets attracting, geometry equilibrium restoration. Electric discharge, potential equilibrium restoration. Chemical reactions, energy equilibrium restoration. Every single one. No matter what example I considered, I always ended up with equilibrium as the fundamental driver, seeking equilibrium, and force as the thing we measure during the process. Which made me realize standard physics has the causation backwards, because I looked it up. They think forces exist first. Forces combine. If they balance, you get equilibrium, like ingredients making a cake. But that's not how it works, because look at the second law of thermodynamics. Equilibrium seeking happens spontaneously. No force is required. Look at all the examples I gave you. There's no force required to drop a rock. It just happens. No external input is needed. So the actual sequence is equilibrium is the fundamental state. Disturbances create disequilibrium. The system spontaneously seeks restoration. We measure acceleration during restoration. We call that measurement force. Force isn't the cause. Force is the symptom. Force is what we measure when equilibrium is being restored. So if equilibrium is fundamental and not force, what does that even mean? First, it explains why things happen spontaneously. If force were fundamental, you'd need energy input to create forces. You'd need to explain where the forces come from. You'd need a source. But if equilibrium seeking is fundamental, it just is. It's the default. It's what systems do. No energy required. No source needed. The source is basically the fact that they need to remain at equilibrium. And if they turn to disequilibrium, they need to get back to equilibrium. And that creates movement, which creates a force that you can measure. It also explains electromagnetic cosmology. Lindsay Harris's whole framework, 3 phi, 2 phi, asymmetry, toroidal fields, sun forming at the tropics. All of that is pressure in geometry, not forces pushing and pulling. The magnetic field is dielectric pressure releasing. The sun forms where two pressure gradients meet. The planets move along equilibrium paths in the toroidal geometry at the center. Standard physics tries to explain everything with forces: gravitational force, magnetic force, electric force. But Ken Wheeler showed magnetism isn't a force. It's a modality of dielectric acceleration. It's just a technical way of saying it's pressure releasing along a pathway. It's equilibrium restoration made visible. The acceleration we measure isn't force acting. It's the process of restoration. So the whole electromagnetic framework makes way more sense when you stop thinking in terms of forces and you start thinking in terms of pressure, geometry, and equilibrium restoration. Fourth, or third, this is the big one. It explains spillover. This connects everything. See, if perfect equilibrium existed, there's no pressure gradients. There's no disequilibrium. There's no restoration processes. There's no measurable forces. Everything just static, dead. But because of spillover, because nothing syncs perfectly, you never reach perfect equilibrium. You're always slightly out of balance, always slightly seeking, or greatly seeking, always in the process of restoration, which means there are always measurable forces, always pressure gradients, always motion, always change. Spillover ensures perfect equilibrium is never achieved, which ensures the restoration process never stops, which ensures forces never stop appearing, which ensures life. So spillover isn't just about free will. It's about why physics appears the way it does, why we measure forces everywhere, not because forces are fundamental, but because equilibrium restoration and equilibrium seeking is perpetual. And that's only possible because of spillover. So let's get back to that AI overview. It said, force is not a byproduct of equilibrium. That's incorrect. Equilibrium is the result of forces balancing out. And it gave me that egg cake analogy. Eggs aren't a byproduct of a cake, they're an ingredient in making one. Similarly, forces aren't created by equilibrium, they must exist first and balance out for equilibrium to occur. But that analogy doesn't work, because you do have to add eggs to make a cake. That's external input. Someone has to crack the eggs, mix them in, bake it. But you don't have to add force for a helium balloon to rise. You just let go, and it happens spontaneously. So the better analogy would be water flowing downhill isn't a byproduct of the valley, but the valley and the water together create the flow we observe. The valley is the pressure gradient, the disequilibrium that it causes. The water is the medium seeking equilibrium that's within the valley. The flow is the restoration process. And what we measure as force is the acceleration of the water, the force of the water as it moves. It's just the effect of equilibrium seeking, not the cause. The valley doesn't push the water. The water doesn't pull itself down. The flow just is. Because that's what equilibrium seeking looks like in a pressure gradient. So the AI had it backwards. Standard physics has it backwards. Force isn't the ingredient that creates equilibrium. Equilibrium seeking is the fundamental process that manifests as measurable force. And I think that's a pretty big deal. Because if you get the causation wrong, you're building all your models on a backwards foundation. Now, I'm not the only person that's realizing this. Ken Wheeler, Theoria Apophysis, has been teaching this for years. He says magnetism doesn't attract. Magnetism is the modality of dielectric acceleration. What does that mean? It means the dielectric field is pressure building, incoherence increasing, like compressing a spring. The magnetic field is pressure releasing, coherence restoring, like the spring expanding. What we measure as a magnetic force is the acceleration that happens during the release. It's not a thing pulling. It's the measurement of the restoration process. And he talks about counter space, which is basically the inertial plane, the dielectric pressure field, the substrate where potential builds. And space is where that potential releases, where it becomes kinetic, where we measure forces. But the fundamental driver is the dielectric pressure, the equilibrium seeking. The magnetism is just how that pressure releases. So Ken's been saying this forever. Magnetism isn't a force, it's a modality. It's a pathway for a pressure release. And I think he's right. And I think the same principle applies to everything. Gravity, electricity, heat, motion, all of it. Equilibrium seeking manifesting as measurable acceleration. Not forces creating equilibrium, but equilibrium seeking creating what we measure as forces. So yeah, Ken Wheeler gets it. Lindsay Harris gets it. And standard physics needs to catch up. Okay, so what do you do with this? How does this change anything practically? Well, first it changes how you think about physics. Instead of asking what force is causing this, you ask what's the disequilibrium and how is the system seeking restoration? Rock falling. Old question, what force is pulling it down? New question, what's the equilibrium state and how is separation from that state being restored? And suddenly it makes more sense because you're not looking for some invisible force entity, you're looking for pressure gradients, geometry, density distributions, actual structure. Second, it explains why ancient cosmologies made sense. They didn't talk about forces, they talked about balance, equilibrium, harmony. The celestial spheres weren't held up by forces, they were in their natural positions, equilibrium configurations. And that actually makes more sense than the modern view, because if you need forces to maintain orbits, where's the energy coming from? How do they not run out? But if orbits are equilibrium paths in toroidal geometry, no energy needed. They just are. I don't know, I'm just thinking out loud here, but it feels like the pattern might extend beyond just physics. If equilibrium is fundamental, maybe it's fundamental to everything, including consciousness. Anyway, that's where I'm at with this. So to summarize, I got into a Facebook debate where I said force is a byproduct of equilibrium restoration, and then they said I was wrong. I looked it up on Google and AI said I was wrong. When I looked at actual examples, helium balloons rising, rocks falling, gases spreading, heat flowing, waves oscillating, magnets aligning, every single one explained better by equilibrium seeking than by forces. The second law of thermodynamics says equilibrium seeking happens spontaneously. No force is required. So why would other equilibrium seeking processes require forces? They don't. What we call force is just what we measure during equilibrium restoration. It's the effect, not the cause. It's the symptom, not the source. It's the cooking process, not the ingredient. And I think standard physics has this backwards for as long as they've been using force-based models. Which might be why so many things don't make sense in modern physics. Why they think dark matter and dark energy and all these fudge factors exist, because the foundation is backwards. Anyways, that's what I wanted to share. Force isn't fundamental. Equilibrium seeking is fundamental. Equilibrium restoration. And spillover ensures equilibrium restoration never stops, which ensures forces never stop appearing, which ensures life. This is an intelligent system. And if that doesn't blow your mind, I don't know what will. But Dusty Truth signing out. Let me know what you think. Do I have this backwards, or does standard physics? I know. Who am I to test physics? I'm just a regular guy. I'm pretty sure it's them, but I'm open to being wrong. Leave a comment, talk about it. All right, Dusty Truth signing out. Peace.